Welcome. I'm Dr. Morton, and I'm going to do a video here on Logic Design Chapter 7. So that's what we'll be covering. Let me shrink myself down. All right, so Chapter 7, we're going to try and sort of lock in and review and extend the concepts for combinational design. The idea is, and this is kind of the cover picture, we have some number of inputs, we have some number of outputs. I'm showing one here, 3 inputs, but it could be more, it could be less, could be more outputs, couldn't be less, I guess. In this case, I'm showing a switch here. That's a hex switch, or even a decade switch. And as you turn it around, it selects the numbers, say 0 through 9, or maybe 0 through F. And then it goes into this network. There are 3 bits here. So 3 bits could give up to 8 different values. So really, we can just do 0 through 7. And then this goes into a network, and then the network drives the 7 segments of this LED 7-segment display. And in this case, we've selected a 6. The network works it out to turn on all the correct segments to display a 6. And so that's just a little example. So in this case, we would have 7 outputs, 3 inputs, and here's our network. And it might be, this is just notional, there might be more AND gates, and certainly there are more output gates because we have 7 outputs. Okay, so let's still go to learning objectives. Want you to be able to list and perform the basic steps in a simple combinational design. And then I want you to be able to describe and work through 2 methods of simplification of a combinational design. One method would be switching algebra. One method would certainly be K-maps, assuming they would apply. Explain why don't cares can arise in a combinational design and how they can help with simplification. We have talked about this before. This is a sort of a repeated learning objective. And finally, describe how to realize the design in hardware in both a AND/OR, which is SOP, or AND, which is POS network. Of course, the AND/OR uses the min terms, and the OR/AND uses the max terms. And then we have some new terms: combinational design, propagation delay, 2-level networks, inputs and outputs. I've used all these terms before, but hopefully you're becoming more aware of them. All right. So here are the steps. We just wanted to point these out. So the first thing we did, we define the inputs. What are the independent variables in this combinational design? And what outputs do we want to generate? So we're going to have n inputs and m outputs. So our truth table is going to have 2 to the n rows based on the n inputs. And it's going to have n columns for all the n inputs plus m columns for all the outputs. So the number of columns will be n plus m, and the number of rows will be 2 to the n power. Determine the form of the solution. This is more of a traditional concept because in the kind of the modern world, if we're, say, designing an integrated circuit, or we're designing or we're programming, we're creating a bit file to program a field programmable gate array, our integrated development environment might very well make some of these decisions for us. Then we will attempt to minimize the logic expression if possible. Again, the IDE may do this for us or may help us with this. And then finally, we would enter the design using our hardware description language into an IDE. Now, these steps are sort of interactive. And then finally, complete the design in the integrated development environment and generate the bit file for, say, programming an FPGA or the steps for making an integrated circuit. Now, obviously, there could be situations where you might still use discrete components and not make a brand new IC because that's expensive, and if you're only doing it once or twice, and it might be a simple enough circuit you wouldn't want to spend the money on a large field programmable gate array. But there are smaller programmable logic devices that you might consider if it is sort of a medium complexity. But if it's super simple, maybe you could just use a few gates. That's possible. All right, so those are the steps. And these are somewhat arbitrarily broken down, but I wanted to give you sort of a little bit of a thumbnail sketch of how to think about the overall combinational design. All right, so here's our standard concept. We have inputs, output, and a network. Remember, for combinational designs, the outputs only depend on the current values of the inputs, and all these variables are either true or false, zeros or ones, ground or say 5 volts, or ground and 3.3 volts, or whatever power the system is using. Might be 1.8 volts, might be 1.1, might be 0.8. There are several different families out there for various integrated circuits and logic devices. All right, so here's an example of a truth table with 3 variables and an output. We'll write the min and max expressions for this. This is just one example. We could use anything. So if we do the min terms, which rows would we select to take the min term from? Well, we know that the min term for the row 0 would be A prime, B prime, C prime, and for row 1 would be A prime, B prime, C, and for row 2 would be A prime, B, C prime, and for row 3, A prime, B, C, and then finally A prime, B prime, C prime, and all the way down to A, B, C. Did I say this would be A, B prime, C prime? Yeah. Anyway, but it turns out that the only rows where the desired output for F is a 1 are the last 3 rows, which means those are the min terms we're going to select: min term 5, min term 6, and min term 7. So that would give us A, B prime, A, B prime, C, A, B, C prime, and A, B, C. And there we have our SOP expression. And we can simplify it by using theorem S1 and applying it a couple of times, and we get AC plus AB. We can combine these two to get AB, and we can combine these two to get, we can combine these two to get AC. So AC plus AB. Again, you can use terms twice. You can use terms as many times as you want. Now, if we want to convert this to the POS form, we could do it directly by writing out the max terms and simplifying it. Or since this is fairly simple, we can factor out the A, multiply using the first distributive law, and write A times the quantity C plus B, which is now in POS form. So that's a very simple transformation. Okay, so we could have also used a K-map, and if we did the K-map, we could plot the last these ones. Again, these are min terms. So this is min term 0, 1, flip the rows, 2, 3, then over here 4, 5, flip the 2 bottom rows, 6, and here is min term 7. So we circle these 2 ones as one group, we circle these 2 ones as one group. Remember, we can't have groups of 3 or any non-power of 2. So only groups of 1, 2, 4, 8. In this case, it goes up to 8. If you had a bigger map, it might be 16, and so forth. And now we want to read these off. So we use our alternate labels. This column is A. The bottom 2 rows are B. The top 2 rows are B prime. The middle 2 rows are C. And the top row and the bottom row are C prime. And then obviously the yellow column is all A prime. So since these are all in the A row, they're all going to have an A in the term. Since they're groups of 2 boxes, we're going to drop 1 term. And we have a 3 variable problem, so we're going to have, these are going to be 2 variable terms. And since the 2 ones here in the middle, here B is 0, or it's B prime, here it's B, so B is going to drop. So this is just going to be AC. And this one down here is just going to be AB. So it's going to be AC plus AB. And that's what we got right here, AC plus AB. And if you wanted to do the zeros, then you'd get this whole row, and you get these 2. So you'd have one 4 variable term, which would be a single variable, and one 2 variable term. And that's A times B plus C. All right. And here are the circuits. The SOP form would look like this, and the POS form has this single A by itself, so there's no OR gate for that. And then you'd have this. Now, you do have to keep in mind that changes in B are going to take longer to affect F than changes in A. And if that's a problem, you might have to put a buffer stage in here, or essentially a fake, or just a OR gate with say two inputs tied together and A going in as essentially a single input, and that would be fine too. All right. So if you look at this, which one of these has the greater cost? Well, it's pretty obvious that we have 3 gates here with 1, 2, 3, 4, 5, 6 inputs. Here we have 2 gates with a total of 1, 2, 3, 4 inputs. So 2 fewer inputs, 1 fewer gate, same number of levels. Clearly, in this particular case, our POS solution with the max terms is simpler. But that's, of course, not always the case. Sometimes it'll be the SOP, and sometimes they'll be equivalent in their cost. All right. We've already talked about functionally complete two-layer networks. So I don't want to spend a lot of time on this again. But what's really important is to understand how we can write these things and how we think about them. So let me switch to the drawing. I want you to look at this figure for a second, and then I'm going to switch over here and draw a little bit. Okay, so the 4 gate types that we like to keep in mind. Let's see, I guess I knocked this crazy here. See if I can. Yeah, that's pretty good, I think. Okay, maybe. All right, something like that. Okay, so here we go. So we're interested in AND, NAND, OR, and NOR. These are our 4 gate types, and we know that with these there are 8 nets, or 8 combinations of 2-layer networks that are functionally complete. So we want these to be functionally complete. And so we have AND, NAND, OR, and NOR. All right. So here's where I want you to pay attention. I'm going to put all of these in parentheses, and I'm going to use an example with A, B, and C. Okay, so normally we would just write A times B times C. That would be an obvious AND gate. I'm going to put parentheses around it. But a NAND gate is exactly the same thing. A, B, C. We don't really need the dots. With a prime on the parentheses, which basically means we invert the output. An OR gate would be A plus B plus C, and a NOR gate would be the same thing, but with a prime on the output. A plus B plus C, and a prime here. So notice these 3 forms, and these you need to be able to recognize. You need to be able to recognize an AND gate, a NAND gate, a NOR gate, and an OR gate. We're not going to use exclusive ORs in this, although they do have canonical forms. And yeah. Okay. So if you think of all the possible combinations of AND, NAND, OR, and NOR, it turns out that there are these 16 different ones. Some of them are functionally complete, and some of them are not. And how can you tell which ones are functionally complete and which ones aren't? Well, all you have to do is use the double inversion technique and switch them back into either an OR AND or a AND OR form. Are 2 standard canonical forms, SOP and POS. And if you're able to do that, then we know that AND, OR, and inverters give us functionally complete set of gates. So if you can get them back into the AND, OR, and the inverters are just, that's where the primes come in. We just use those wherever we want. Then we know that's functionally complete. If they only reduce to either an OR gate or an AND gate, then it's not functionally complete. So let's take an example. So we know, for instance, that we know, for instance, NAND is a functionally complete set. All right. So let's see. So NAND functionally complete. Okay, let's see if that will, if we can switch that back into an and or form or an or and. It turns out it'll switch to an and or form. Well, yeah. All right, so let me switch back to my paper here. All right, so I'm going to take, so I'm going to do and. Maybe I'll just do a couple of variables. So I'm going to, so NAND. So I'm going to do A prime, B, C. That's a NAND gate. Let's see, and then we want to do NAND, so we'll make another one times A C prime times B C prime. All right. Now, and put ticks on all these. Okay, so I just made, we'll say that equals F. So I just created this, made it up. It's no big deal. Okay, let's see if we, this is in, oh, I have to do one more thing. I have to put in a set of parentheses on the outside. So each of these is a NAND gate because it follows this form right here. And then the whole thing is one big NAND gate because it follows this form as well. We have this, ANDed with this, ANDed with this, and then the whole thing inverted. So we should be able to convert this back into a and or form, and that will tell us if in fact this is functionally complete. And if we can't, if it doesn't convert back that way, then we'll know it isn't. Well, so how do we do that? Well, the first thing we can do is we can bring this tick mark in to all these, and what we'll do, we'll treat this just like it was X, Y, Z inverted. So if we bring this in, we would wind up with this. It would be equal X prime plus Y prime plus Z prime, because remember we have to change the implied AND functions here into OR functions, and we have to prime all the variables. Well, we would do that. So our X is just going to be the quantity A prime B C primed, and so if we do this, what we're going to get is we're going to get A prime B C without a prime plus A C prime plus B C prime. And now you see we have AND gates and one big OR gate. So this is an AND OR form, or its SOP form. So we know this is functionally complete, therefore we know that NAND is functionally complete. I dropped something off my desk, but I can't find it, so I'm not going to worry about it. Okay, so let's try one of these others. Okay, why don't we? So we know that a NAND OR is not functionally complete. So let's see what happens if we write that out. So here's a NAND. So we're going to just write we'll use our NAND expression. So we'll say A, B, C inverted, and then we'll have the output gate OR, so we'll have some pluses in here. We'll have A prime, C prime, and maybe we'll have another one with a tick here, and maybe we'll have another one, B prime C, and we'll have a tick there. Maybe we'll do B prime C prime, who cares? All right, and we'll say that equals F. Okay, we just made this up for purposes of demonstrating. Now let's see what happens if we try and simplify this and see what happens. Well, the first thing we do is just take these ticks in here, and that would give us A prime plus B prime plus C prime quantity plus A plus C quantity plus B plus C quantity equals F. And you can take away all the parentheses and you just wind up with A prime plus B prime plus C prime plus A plus C plus B plus C equals F. Okay, this is just one big OR gate. That's all it is. So, oops, you can't quite see that, sorry. So that's just one big OR gate. So it is only an OR gate. Well, an OR gate by itself is not functionally complete. But an AND/OR is functionally complete. So we can represent any logic expression in NAND/NAND form, but we cannot represent any logic expression in what we set up here, which was NAND/OR. And if you look back at the book, you can see that NAND/OR is not one of the ones with an asterisk. The ones with the asterisks are functionally complete, and the ones without aren't. And here's a little table that shows the combinations. Now, what this shows, and this is important, is that we can start with SOP, and we can do a double inversion, and we can partially expand that logic function, and we can go in this circle. So we go AND/OR, we partially expand it to NAND/NAND. A little bit more, we get OR/NAND. A little bit more, we get NOR/OR. And if we do a little bit more, we're back to where we started. Because remember, if you do a double inversion, you won't have changed anything. Same with the POS. It turns out if you want to get from the SOP form to, say, a NOR/NOR form, the first thing you have to do is convert the SOP form to the POS form. And then you can do the double inversion, and you can go through all these possibilities. That's also true graphically, and so I'm gonna try and demonstrate that now on paper here. First we'll do it with algebra, and then we'll do it graphically. All right, so let me do that. Okay, so I'm gonna get rid of this. All right, so let's start with we'll start with an AND/OR form, which is SOP, if you remember. So we're going to do, we'll do A, B, C plus A prime, C prime plus B prime, C. Something like that. Maybe we'll do something like that. All right. And this is going to equal F. The first thing we do, if we want to convert this to the different forms, is we do a double inversion. So we do parentheses, and we do one inversion, we do another set of parentheses, and we do another inversion. Since we've double inverted it, we haven't changed anything, because we know if you invert something twice, you get back to where you started. All right, now we'll take this inner inversion, and we're just going to move it in here. And before we do that, though, we'll rewrite it. So we'll rewrite ABC, and we'll put that in parentheses, plus A prime C prime, parenthesis, plus B prime C in parentheses. And then we'll do our double inversion. Equals F. Now we'll apply this in here. So we'll, rather than breaking it into all these AND gates, what we'll do is we'll make these into NAND gates. So we'll put tick marks on these. We'll get rid of this, and we'll change all of our operators from pluses to times. So what we have now is ABC prime, or sorry, ABC quantity primed times A prime C prime quantity primed times B prime C quantity prime, and then the whole thing prime. Now, if you go back to the form we looked at earlier, which is right here, notice for AND gates it looks like this. For NAND gates it looks like this with a tick on it. For OR gates it looks like this, and for NOR it looks like this with a tick on it. All right. So if we look at this, what kind of gate is this? Well, that's a NAND. That's a NAND. That's a NAND because of these ticks. And then the whole thing is really like it's really like X, Y, Z with a tick, because this and with this, all with a tick on the output, represents another NAND gate. So this is in NAND form. Now let's set this up in a graphical manner. Okay, so let's say we have our initial one. We're going to have 3 AND gates. Okay, and this is going to be this will be ABC, 3 inputs. This is going to be A prime C prime, and this is going to be B prime C. And these are going to go into one OR gate like this. And this is going to be F coming out. Now, remember how we can substitute in alternate symbols for these gates. Remember, our alternate symbol for an AND gate is an OR gate with inverters on all the inputs and all the outputs. And the symbol for a OR gate is an AND gate with inverters on all the inputs and the output. So in this case, let's hang on 1 second. All right. So in this case, let's just substitute for this OR gate. So remember, we can substitute an AND gate in with 3 inverters on the input and 1 on the output. So that's going to look like, it's going to look like an AND gate here, an AND gate here, an AND gate here, and then this gate down here with 3 inverters on the inputs and 1 on the output. And this is still going to be A, B, C, A prime, C prime, B prime, C. And then this is going to be F. Now notice, remember the rules about bubbles? Oops, you can't see, sorry. Remember the rules about bubbles? I can take the bubbles and I can slide them. So I'm just going to slide this bubble up to here. I'm going to slide this bubble up to here. And then we get rid of the bubbles down here. And then I'm going to get rid of these. I'm going to cross out all these bubbles and slide them. And I'm going to leave this one alone. Now, if I redraw it, and this is again A, B, C, A prime, C prime, B prime, C. Now, what type of gates are these? These are all NAND with input gates and a NAND output. So now I have a NAND 2-layer network. And I did it algebraically and I did it graphically. Here it is algebraically, here it is graphically. So you can do this either way, but you can definitely convert. Now, what would happen if I did more work? Well, it turns out if we keep going, if I did a little more expansion, I'd be in OR NAND form. If I did a little more expansion, I'd be in NOR OR, and if I did a little more, I'd be back in my original form. I'm not going to go through that in the interest of time. Okay, so again, these are the alternate symbols, and we just use the symbol for an OR gate was an AND gate with bubbles on all the inputs and the output. Now for a NOR gate, there's just bubbles on the inputs, but we can substitute these gates. Again, this is the NAND gate. That's the AND gate. That's the OR gate. That's the NOR gate. All right. Sometimes we might want to expand to more than 2 layers. And we do this little equation here is kind of an example of that. If we factor this A out, it can really simplify this expression a little bit, because then we only have gates. We have 3 gates with 3 inputs, and then 1 output gate with 4 inputs, as opposed to 3 gates with 4 inputs and one output gate with 3 inputs. So it saves us some inputs. It doesn't save us any gates in this case. There are also times where it definitely can save us gates. So sometimes we will expand to 3 layers just to save some hardware where we don't care about the extra delay time through the network. The reason why there's an extra delay time is because we have 3 layers now. Okay, yeah. Let me just show that so you're convinced. Okay, so I'll do it up here. So we took, our original was A, B prime, C, D, A, B, C, D prime, and A, B, C, D prime. Oh, no, this is B prime. Sorry, this is B prime. And then we had one output OR gate. Okay, and then this is F coming out here. All right, now when we factored A out, what we wind up then is with, we still have 3 AND gates. And this is B prime CD, B prime, okay, how come I can't? Oh, this was A, B, C prime, so this should be C prime, B prime, C, D, and then B, C, D prime. All right, and then we had one output OR gate down here. These all go into it, and we also have an A going into it directly. And here's our F coming out. So in this case, we don't actually even increase our layers. We just factored out the A. We saved, so now we have 1, 2, 3 inputs, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Whereas here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we do save 2 inputs by doing this, factoring out the A. So that's one example. In some examples, it does actually increase the layers. In this, it doesn't. Yeah, so. All right. So I kind of misspoke. It's a bad example. It's actually, I don't know why it's hard to find good examples of this. Whenever we do this, though, we always want to do it by, if we have an and OR form, then our added layer needs to be an OR layer. Or an AND layer. All right. Well, anyway, okay. Yeah. I will. We'll work some more problems like this. All right. I want to quit with this, and we will pick up again in chapter 8.